Hi, I'm Dave. I'm a Clojure developer from the UK, and I'm a hobbyist programming language designer. I like Lisps, I like writing Lisps, and I like writing Lisps in Lisps. So if you like those things too, just come and talk to me afterwards. I'm sure we'll get along fine. And today I'm going to be talking about one of my favorite things. It's Lisp. I'm going to be talking about Lisp. Probably saw that coming. And in this talk about Lisp, we're going to be writing a program which uses Scheme, Python, and C interchangeably in a single file. Easy, right? Before we get there, first, we'll take a look at some Lisp code. We'll look at its structure and its syntax. Then we'll look at the rules of Lisp evaluation and understand how a Lisp program is actually executed. And finally, we'll take a look at Autology, which is a Lisp that I've written that can modify its own rules of evaluation by rewriting its interpreter at runtime. We'll look at some of the weird and wonderful things that Autology can do. And finally, we'll use Autology to write a program which switches between Scheme, Python, and C interchangeably in a single file. I promise it's going to be good. And while we do this, we're going to be asking ourselves, what is a language in quite an abstract way? Is it the code that we write? Is it the syntax of that code? Or is it the rules of evaluation? Or maybe the interpreter itself? And is that like the source file that contains the interpreter code? Or is it the compiled interpreter executable that we actually run? Or is it some kind of abstract semantic category transcending all of these concepts, which they themselves become increasingly ill-defined as we probe the boundaries and distinctions that separate them? Well, let's start by looking at some code. So here is some code. What language is it in? It's hard to say. It's just the number 4. At this sort of resolution, they all look pretty much the same. Now, this is a valid Lisp expression. We would call it an atom, and that's because it's not a list. Implicitly, then, the other type of expression is a list. So here we have a set of parentheses delimiting our list containing 3 atoms, plus 1 and 1. I realize this is London Clojurians, you probably know this, but we're going to go from the ground up just to make sure everyone's definitely on the same page. This, of course, is actually a function call in Lisp. Whenever we see a list with stuff inside it, we expect the first element to be a function and the rest to be its arguments. Pretty straightforward. These lists can be arbitrarily nested to make complex expressions. This program is a tree of lists, which is a little easier to see if we do this. Evaluating this program does a depth-first traversal, evaluating the individual sub-expressions and then eventually the whole program. This one, of course, returns 15. Now, a depth-first tree traversal is actually pretty straightforward to write recursively. So let's have a look. Here is a Lisp, an entire language in a single function, possibly my favorite function ever. Let's walk through it together so that we're completely on the same page here. We're defining a function called evaluate. It takes 2 parameters, an expression e and an environment env. The expression E is the code that we actually want to run. So this will either be a list-like data structure, like the +1,1 that we saw earlier, or maybe just a single atom. The environment is a map, and it holds the variables and functions that we currently have access to, those that are in scope. If the expression is not a list, then we know it must be an atom. If it's a symbol, a variable name, then we look it up in the environment and return its value. Otherwise, when the expression is not a symbol, then it's just a literal value. It's a number, it's a string, a Boolean. So we can just return that as is. If we are dealing with a list expression, well, we're going to do 3 things. First of all, we're going to evaluate the first element in the list. We're going to assume that this will return a function. And step 2 is to evaluate the rest of the elements in the list. And step 3 is to apply the function returned by the first element to the values returned by the rest. And that's it. You now know how to write your own Lisp. It's a whole language. It's not a very powerful language, but it is a language. And most impressively, it's only 9 lines of code. Well, of course, this is Clojure, so it's actually 1 line of code, but not very easy to see. So this is about as simple as Lisps get. We have the ability to evaluate basic expressions, but not much else. My language, Autology, is slightly more complex. It has a couple of edge cases to the normal evaluation rule of if it's in a list, it's a function call. And in Lisp, we call these special forms. First of all is the ability to define variables with the special form bind. Here we supply a list of symbol-to-value binding pairs and then a body expression. And the bindings are only available within the scope of this bind expression. This should probably feel reasonably similar to Clojure's let or any other Lisp. We also have the ability to quote an expression with qu. This means we don't want to evaluate the expression, but just return it as is. This is helpful for building up expressions. And that's it. This is the Autology language so far. We can evaluate atoms. We can evaluate lists as function calls. We can bind new variables, and we can quote expressions without evaluating them. Now, the decisions we've made with our language here are completely arbitrary. You could use any name you like for the special forms, and you could structure the syntax differently too. So let's take a look at a couple of small tweaks that we could make to our interpreter. We currently use the classic Lisp prefix notation, where functions are the first element in the list. And this is implemented by the function application section of our interpreter. When we evaluate the first element of the list, and then apply it to the results of evaluating the rest of the elements. But if we wanted our language to use infix operators, which some would argue make maths expressions a little bit more intuitive, we can modify our function application code. So we simply apply the second element to the first and the last. Of course, in this instance, this modification only works for functions with exactly 2 arguments, so it's a little bit limited. Another tweak that we could make is to implement a basic form of tracing. Here we have a condensed version of our original interpreter. And all we need to do is print the expression E before we evaluate it, like normal. Now, when we evaluate an expression, we print each sub-expression in the order we evaluate them before returning the final value. So we have our interpreter, and it's a function, and it takes a tree of lists representing some program that we want executed. But our interpreter is also written in Lisp, so it too is just a tree of lists representing a program that we want executed. This is a data structure that we've already shown our language can quite easily handle. So now, instead of our interpreter being a defined function, let's take the literal data, which represents the interpreter as an anonymous function, store it in an initial interpreter variable, and then stick that in the execution environment under the special symbol I. We'll also be adding a bunch of normal functions to the environment so that the programmer has something to work with to build their programs. Now we'll define a new evaluate function, which first grabs the interpreter data from the environment and then uses the parent language Clojure to evaluate it into a callable function, and then uses this to do the actual evaluation of the expression. Now, what does this do? Well, nothing by itself. The language works just as it did before. But instead of our interpreter being a function, it's now stored as the data that represents a function and is turned into a function each time we want to evaluate an expression. However, we now have access to this special symbol I inside the programs that we're writing. It's in the environment. It's always in scope. If we were to rebind this variable to a new tree of lists that represent a different valid interpreter function, then any code within the scope of that binding will be evaluated using that newly provided interpreter. So this new interpreter completely ignores both the expression and the environment and always returns the number 42. Is this useful? No. Is it a language? No. Yes. Debatable? How can we make this better? Well, first of all, writing a whole new interpreter every time we want to modify the language is a massive pain. So Autology provides a couple of helpful mechanisms to make things easier. First of all, our actual Autology interpreter looks like this. And don't worry, we're not going to go through the whole thing, since it's actually not meaningfully different from the minimal Lisp we already looked at the beginning. But if we just take a look at a small section, we can see that the different sub-expressions of our interpreter are tagged with these little ATL markers. These markers label the different sections of the interpreter and give us an easier way of referring to and modifying different parts of it. And Autology provides a couple of utility functions that use them. We have a get marker, which for a given interpreter and marker will return that data structure, that section. And we have replace marker, which takes an interpreter, a marker, and a new data structure to insert in place of the original marked expression. Okay, with this, we can actually start to do something for real. Autology is actually missing a feature that many other programming languages have out of the box. Functions. There is initially no way to create a function in an Autology program. Now, I don't know about you, but I have personally found functions to be actually quite useful from time to time. So let's modify Autology to add the ability to create them. First, we're going to grab the eval list section of the interpreter. This section of the interpreter is responsible for evaluating lists, and it consists of a case statement switching on the first element of the expression being evaluated. Each special form is a test value and a result expression, with the final default expression at the end with no test value. Now, to add a new special form, all we need to do is insert a new test value and result expression before that final default expression. So we'll grab that eval list section and bind it to a variable called original. We'll then define the new special form, a quoted list containing our test value, the lambda symbol, and our result expression, which is what actually handles the creation of a function. Then we're going to rebind I, replacing the eval list expression with a version where we splice in our lambda special form before the default expression. And now we can just straight away use this new feature. So here we can create a function called double. We'll bind this symbol to a function using our new lambda special form. It takes a number n and adds it to itself. Then we can immediately invoke this new function a bunch of times to end up with a predictable answer. Now, the fact that this fits on a single slide is, I think that's really cool. We have a language here that does not have functions, and yet somehow does have the ability to modify itself so that it does have functions. I think that's wild. And rather delightfully, for this whole part of the program, you cannot create functions. They don't exist. Then, as soon as I has been rebound here, you can, completely naturally. We haven't even left the binding pairs when we do it. And of course, once you leave this final parentheses, functions once again no longer exist. We're back to plain old original Autology. But hopefully by that point, the programmer has already written all the functions they're going to need. The other mechanism that Autology provides to make this meta interpretation easier to use is a special form in the interpreter itself called withI. This special form is similar to bind in its structure, but it only binds to the special I interpreter symbol. And it allows you to bind a pre-existing interpreter so that you don't have to actually define it within your Autology program. Now, for the most part, this is actually just for convenience. Pretty much anything that you could do with this special form could also be done manually by rebinding the interpreter in the program. But sometimes that's a bit of a hassle, especially if you're switching back and forth between multiple different interpreters in the same program. So here is a program that switches in and out of using a pre-built debugging interpreter that I've written. We start by binding a local variable pi, and then we begin adding some numbers together. Then we're going to switch into this debugging interpreter while we evaluate this 3, 4, 5 sub-expression. Then we go back to the initial interpreter while we bind another local tau and evaluate 6 plus 7. And then finally, we switch back into debug mode to evaluate the 8 and 9 expression. I think the easiest thing to do here is actually just to run this program. So let's give that a go. Cool. So I'm going to run this debugging.atl program, and it's immediately going to pause evaluation when it gets to the first with I debugging section. Here it shows us that it's going to be evaluating this +3, +4, 5, and we can step through it one by one as it evaluates the different sub-expressions inside that expression and goes through it as a normal debugger would. While we're doing it, we can press L to print the local variables. So we've got pi there, nice. We can carry on going until we leave the first debug section and skip forward until we get to the next one. Here we can print the locals again, and we see that we got pi and tau. And also while we're here, we can press E to evaluate an arbitrary expression in the current scope. So we can say, let's plus pi and tau and 10 together, and it's going to tell us that's 19.42. Very useful, very cool. We can carry on going until we get to the last, and then it will return our value of 42. Fantastic. So hopefully you'll agree that that is a pretty fundamental and drastic modification to the base Autology language. But why would we want to modify our language? I mean, Autology is great, right? It's a Lisp, it's functional, it's pure. These are great things. No one would argue against that, right? But every now and again, it is a little difficult to express things in its single body expression, anti-imperative, pure functional style. So what if it wasn't pure? What if it wasn't functional? What if it wasn't a Lisp? Here's an Autology program that uses a predefined scheme interpreter. Now, scheme is another Lisp with a famously minimal specification. So writing a fully compliant interpreter for it is actually pretty straightforward. In fact, before this, I actually just copied the scheme implementation from SICP verbatim and just translated it into Clojure and stuck it in. So because of this, in quite a real sense, we are actually writing and executing genuine scheme code here, which I think is kind of cool. Well, what else can we do? Here's an Autology program that is using a predefined Python interpreter. Well, Python is an interpreted language, right? So this isn't too strange. This Python, though, isn't actually a full implementation of Python. It's just enough to get the very basics, like variable assignment, arithmetic, and function calls. Although it does actually have a notion of libraries, which contain functions, and importing and aliasing these libraries works in a simplified but reasonably accurate way. Of course, our NumPy library here also isn't fully implemented either. That would be a lot of work. It just has the array and product functions inside it. But this highlights something quite cool. You only need to implement the aspects of a language that you actually intend to use. Presumably, the programmer in this instance really likes the way that array products are expressed in Python with NumPy. So they implemented the minimal viable interpreter, and now Autology becomes expressive and concise in the desired way. Let's take it one step further. Here is an Autology program which uses a predefined C interpreter. Now, the eagle-eyed among you might have noticed an issue here, which becomes apparent if I switch to Clojure syntax highlighting. That's right. The semicolon end statements in C are considered inline comments in Clojure. Perhaps unsurprisingly, there are some pretty fundamental conflicts between C syntax and parsable Clojure expressions. And also, even if you separate each of the for loop header sections onto their own lines and start the code block beneath it, it still thinks the code block is a Clojure map literal, and it complains that it has an odd number of forms. Oh well. Autology gets around this with a custom read function that essentially captures everything within the body of a with I expression as a string. And it just assumes that when we get to evaluating this sub-expression, the currently bound interpreter will be able to handle it. But it works. This program actually does print hello world, and it does simulate the imperative stateful for loop with all of its assignments and mutations. It's a bit strange since it's an interpreted C rather than the compiled C. Although theoretically, it would be possible for Autology to modify itself so that it reads in a C program expression, actually compiles it with appropriate system utilities, executes it on the host system, and then returns the value to the running Autology program. I've not done this, but if you think that sounds fun, the Autology repo is very open to pull requests, so please. And finally, there's absolutely nothing stopping us from doing this. Since each of these programs just returns a number, we can wrap them together in a single call to plus. And this works. Is it beautiful? Is it heresy? Those are both opinions, and Autology doesn't care. This program prints out hello world and then returns 126. So this brings us to the point of the language, or at least as close as I've been able to come to a reason something like this might actually be a good idea. Different languages have different ways of expressing things. Each has its own advantages and disadvantages. Many are designed to work particularly well in some specific domain, or to embody a specific programming paradigm, or even to tackle a very specific niche of algorithmic computation. Autology asks the question, why not pick and choose which language features make the most sense at every point? Mix and match languages a la carte, and always operate in the syntax and semantics that make the most sense and give the most clarity. Of course, the reasons not to do this are manifold. The complexity of the system skyrockets, the efficiency of the code plummets, and the maintenance of the code base becomes a literal nightmare of context switching, which I would not wish on anybody. And anyway, interoperability between languages already exists in a more limited, structured, and arguably safe form. With a good foreign function interface library, you can write the hot code of your tightest loops in C and then trivially call it from almost any language these days. So what benefit do we gain from doing this with Autology? And is it worth making syntax highlighting so unreasonably difficult? Well, because with Autology, we're not actually limited to languages that exist. So let's do it. Maybe you love for loops in C. Sure, totally cool. I don't judge. Nice. But why not try this with Haskell's range syntax? And while you're at it, maybe we should use Python's for-in structure. Well, that feels good. Hey, why not Rust's Unicode support? Oh, okay, not that one. That's awful. But the point is, we don't have to limit ourselves to using a single language like we would with FFI. We can blend aspects of existing languages together at will and even implement completely novel features at the same time. Now, a common question I get asked is, can't you just do this with macros? It's a very understandable question, as macros are the normal choice for language extension and syntax modification in Lisp. And yes, many of the things that you can do with meta interpretation can be done with macros. However, these two forms of metaprogramming operate with quite different characteristics. For instance, macros are defined in code and are expanded at read time, while meta-interpretation happens at runtime and could theoretically allow modification of the interpreter using data from the file system, from a user prompt, or even from a web request. Macros are limited to parsing readable data structures, whereas meta-interpretation can handle anything that you can put in a string. And finally, macros are kept hygienic by using gensims for internally created symbols, so we don't end up leaking and capturing existing scoped variables. Meta-interpretation doesn't care at all, and often actually relies on references to symbols which are assumed to be in scope. We're essentially evaluating arbitrary user-provided data structures, assuming their functions, and then using them to evaluate arbitrary code. Nothing about what we're doing here is safe, but it's still okay. So what else can we enrich Autology with? Some other languages have really cool features which would allow your Autology program to be much more expressive, more succinct, or more powerful. What about the pattern matching of Erlang? Or the continuation passing style of Scheme? That'd be good. But whatever we add needs to be worth a lot. since the overhead of modifying the language is pretty huge. What if you wanted to add a custom data visualization tool, which is really specific to the domain that you're exploring? Or some custom debugger keeping track of the stack frames and state of your programming, allowing time travel? Sounds cool. What if we abandon all reason and really push the concept to its limits? Well, hypothetically, every program in every language is an autology program, given some appropriate boilerplate to set up the interpreter correctly. Theoretically, every file on every computer is an autology program, given some nonsensical and arbitrarily defined interpreter rewriting. All right, what about something even less sensible? Let's consider a static file containing 1,000 random bytes. First, we can modify an autology interpreter to treat this file as a valid program. Let's say one which calculates the 20th Fibonacci number. Then we can modify a different autology interpreter to also see this same file as a valid program, but a different, say one that finds the 20th prime number. Now, this is silly, right? It's basically pathological. We're effectively writing the language to fit the code which already exists. But then, isn't that what we should be doing? I mean, it's certainly similar to what I do when I'm planning a new language. I write snippets that demonstrate the type of expressiveness I'm after, and then I write the interpreter to fit. It also has a parallel with test-driven development, where you define the assertions you want to hold true and then implement the code to match. It's the kind of thing we even do on a more granular level, that of individual functions, especially ones that abstract some level of complexity. Admittedly, in this case, we're probably taking it a bit far, since we're basically ignoring the input program. Now, let's quickly take a step back, zoom out, and look at this interplay between language and program at a slightly more general level. Here we have a diagram depicting some arbitrary computation. You might have to use your imagination a little bit. When we want to achieve some computational goal, we use a combination of a language and a program. And it's up to us to decide where the computation actually happens. If we encode the computation directly into the language, we end up with something like the random bytes example. And the program is essentially meaningless, as evidenced by the fact that we use the same input program for both languages. Whereas we could go completely the other way, define almost nothing in the language and do all the work in the program. In that case, we'd likely be talking about some kind of machine code written directly on the metal, or even using something like the lambda calculus if we wanted to ignore the substrate that we run on. In either case, the language defines only the simplest mechanisms by which general computation can be achieved, and then everything else is left up to the programmer. In effect, we're basically talking about the differences between high and low-level languages. We just come at it from an unusual starting point. Lambda calculus is the lowest level, and the random bytes interpreter is the highest. So the next time you're writing a DSL, some API, any interface between two systems, or even just a single function, it's worth asking yourself where the computation should live. Is it in the definition of the abstraction itself, or in the use of it? It's at least a good idea to remind yourself of the scope of the options from time to time. Now, what level is Autology? Good question. Well, it's a relatively low-level language in that it provides the minimum basic mechanisms for computation. Well, arguably, even less than the minimum, because it actually doesn't have functions, as we discussed. But it's able to transform itself into the very highest level of language. In this way, meta-interpretation allows you to climb up and down the ladder of language abstraction. You get to choose what balance of language and program is most appropriate for whatever problem you're solving right now, down to the individual S expression. Okay, well, let's take a step back here. Autology is a language that lets you manipulate its interpreter using lexically scoped bindings, allowing you to modify its features and character in an incredibly flexible and powerful manner. The fundamental goal of this project is to expose this novel programming paradigm and to incite introspection into our everyday assumptions about languages, programs, data, and the boundaries between them. The project currently is as simple as it can be, whilst still demonstrating the effects of this interpreter modifying metaprogram. Often this kind of language gets referred to as a toy language, but I think that just because we're not building enterprise applications in it, it doesn't mean that it can't be a serious and beneficial tool for exploring programming language design and, more generally, helping us to take a considered approach to how we think about and implement abstractions, from the smallest functions to the largest inter-system APIs. And definitely not just saying that because writing a proper language is a lot of hard work, and I've already done all the easy and fun bits. There are a couple of areas in which Autology could use some work. The REPL implementation exists, but it's currently very basic. It only allows single line inputs and doesn't have a cursor, so you have to delete stuff to fix mistakes. It's a very poor user experience. There's no way for you to create custom predefined interpreters without modifying the project source code. It would be nice to be able to refer to external files for this kind of thing. There are a million languages which have interesting features which would be fun to play around with, but writing interpreters for these languages, even minimal partial implementations, takes a good amount of effort. And the project does have some helpful example programs which show off some of the things you can achieve with meta interpretation, but I have barely scratched the surface of what's possible in the repo. So if you think you can help make this project more usable, or if you have a favorite language with an awesome feature that you've always wanted to try and implement yourself, or if you've just right now thought of something cool, or more likely pretty stupid, that you can do with interpreter modification, please, by all means, do check out the repo, raise an issue, make a PR, whatever you like. I'm very open to suggestions. Anyway, I really hope this has been interesting. I've had a huge amount of fun with this project. It's definitely something that I'm going to be playing around with for quite a while. It's been really great to have the opportunity to share what I've been working on, and it's been really exciting hearing what people have to say about it.